Lecture 8 covers sections 3.5 through 3.6. At the end of the lecture, you should be able to construct equivalent voltage sources in series, construct equivalent current sources in parallel, and understand the operation of an ohm meter. To begin, let's consider the following circuit. We have an ideal current source providing current to, say, a node, let's call A, at which it's connected to resistor R1, and two ideal voltage sources, VA and VB, and a series configuration that are then connected to resistor R2. Say we want to determine the effect of two voltage sources in our series configuration. Well, we can look at this system and realize that since we have two voltage sources in series, similar to batteries in a remote, that our current has to be the same running through each, i.e., we have to have continuity of current, for we cannot create or destroy charge carriers. That is to say, IA has to be equal to IB. So, we know they have the same current running through them, but what do we know about the voltage potentials being established, say, between terminals A and B? Well, if we do a KVL loop around the right-hand side of our circuit, so in the bottom left-hand corner, and going through our system in a clockwise fashion, we can say minus V1 plus VA plus VB plus V2 is equal to 0. That is, we see that VA and VB add algebraically based upon the polarities, i.e. which terminal we enter first, such that they add in this particular situation. That is, we can express VA and VB in this configuration as V, which is the summation of our two voltage potentials. Therefore, we can construct the following equivalent voltage sources based upon the polarity of our constitutive sources. Based upon the previous example, we are at terminal A and went to terminal B where we had two ideal voltage sources. Recalling when we did our KVL equation, we progressed from A to B. That is, Vs would be equal to VA plus VB. Now say our voltage source VB was switched. As we moved from terminal A to terminal B, we enter a positive terminal and then a negative terminal. If we did the KVL equation, this would be plus VA minus VB. That is, we can say our voltage source, or equivalent, would be equal to VA less VB. Thus, our voltage sources sum in an algebraic fashion based upon the polarity of the terminal we first enter when we do our KVL loop. Now, why can't we have two voltage sources in a parallel configuration? Well, in this class, we assume our voltage sources are ideal, i.e. they're putting out exactly the voltage that we prescribe. However, in reality, there is variance. No two batteries are the same, nor are any two voltage sources. If we have two voltage sources in a parallel configuration, the strongest of these sources will dictate our voltage potential, i.e. it will overpower the one next to it. Therefore, we avoid drawing voltage sources in a parallel configuration, for in actuality we do not know which is the stronger of the two. Now let's look at current sources. We can make the following equivalent current sources based upon the directionality of our ideal current sources. Say we have a terminal A and a terminal B, for which we have two current sources, IA and IB, existing. Both IA and IB are existing in the same direction, such that we can create an equivalent IS, which is equal to the sum of IA plus IB. Now, if we look at the circuit below, where we have a terminal A and a terminal B, we have IA providing current to B and IB providing current to A. That is, our equivalent IS would be IA less IB. Now, the magnitude of IA and IB will determine whether or not IS is going to be in our positive upward direction or in our downward direction. Now, we can only do this for current sources in a parallel configuration. Why can we not have current sources in a series configuration? Recall our continuity of charge carriers. That is, IA might be providing some amperage and IB another amperage. The current running through IA and IB have to be identical, but we cannot increase it going from IA to IB. That is to say, if we have current sources in a series configuration, it violates the continuity of our charge carrier.